This is the SMU Data Science Capstone. Our team is Spencer Fogleman, Sangrae Cho, and I am Jeremy Otsap. Our project is detecting tumors using machine learning. Why? Because 1 in 8 women will get breast cancer. Mammography is the current imaging technique for detecting breast cancer. Accuracy is a problem with these mammograms, as breast cancer is correctly diagnosed in only 78% of the women tested. They can be difficult to visually interpret, which requires additional screening and radiation exposure. Furthermore, certain types of breast cancer cannot be detected with mammography. Now on to Spencer to elaborate on the image set and its preparation for deep learning.
So a version of mammography used in the hospital setting is called digital breast tomosynthesis, also known as DBT. So in DBT, you have a machine that will rotate around the woman and take images of 2D slices of the breast tissue. These images happen at 4 different angles: LMLO, RMLO, LCC, and RCC. And at each of these 4 angles, about 60 to 80 images are produced, and there is a corresponding 3D DICOM image that is created for each angle. So in the end, we will have 4 DICOM images. So the data set we used for our capstone came from Duke University Hospital. And the reason that these files are in DICOM format is that DICOM is a universal standard for imaging in healthcare. And DICOM format allows for the easy transfer of images across the hospital. So the data set had 1 DICOM file per patient per view. So because we had 4 views per patient, we had 4 3D DICOM files per patient. But for machine learning, we actually need to work with 2D images. So the first step in our data preparation was actually converting this 3D image into the corresponding 60 to 80 2D images in JPEG format. So the next step in our data preparation was to split up our total images into a training test and a test set. So in a training test, we use those images so that our model can learn features about tumors. And our testing set is used for evaluating whether or not our model is performing well. So in our original data set, we had 3 types of people. We had a healthy person who did not have a tumor present. We had a person with a malignant tumor, and we had a person with a benign tumor. So in creating our data set, we actually had to do some steps to make it ideal for machine learning. The first thing we had to do was undersample our healthy patients to address for the class imbalance, because most people do not have cancer. The second thing we had to do was actually combine our malignant tumors and our benign tumors into a single class, because we didn't have enough images to identify them separately. And the last thing we did was we needed to discard images that did not have an actual true label, which was associated with the biopsy result. So in making our split, we had to keep in mind the possibility of data leakage, because there are many photos for a single patient. So in our train test split, this would have been a bad split, because we had multiple images for the patient in our training set, but then also for the same patient in our test set. A better split would have kept all images for a single patient in either the training set or the test set. And what happens is that with a split like this, the model ends up learning information about the patient rather than about the tumor, and this leads to results that are overly optimistic and do not generalize well to new patients. So the model we decided to go with was a convolutional neural network, or a CNN. And in a CNN, the input feature is a 2D image of the breast tissue. And this 2D image gets fed through a neural network. And first, there are filters that go over the image and detect certain features of the image, such as shapes or corners. And then these features get combined to form probabilities about whether a patient will have a tumor or not. Transfer learning is a technique that's very common in computer vision. So in transfer learning, what happens is you take another company's model, such as a model that is used to identify cats or dogs, and we only keep the part of the model that learns lower level features such as shapes. while discarding the parts of the model that are specialized for their own use case. And for us, we replace that with layers in the model that will be specialized for detecting whether a patient has a tumor or not. So in addition to choosing the transfer learning model to use for our use case, we also experimented with other methods to tune our model, the first of which was data augmentation. In data augmentation, an image is flipped or rotated, and this prevents overfitting so that the model can generalize to new patients. The next thing we did was we experimented with changing the input image dimension. The last thing we did is we experimented with changing the number of images per patient, so whether to include all hundreds of images associated with a single patient or just to pick a single image associated with that patient to put in the training set.
Let's talk about the strategy and method. Strategy number 1, multiple slices of image per patient, and image size is 2 to 4 times 2 to 4. The first transfer learning model is VGG16 as baseline, and the accuracy is just below 54%, and the bottom plot shows the model is overfitting. The second transfer learning model is adding augmentation to fix the overfitting issue, and the accuracy is just below 61%. The third model, we added more epochs, but the accuracy actually went down. The fourth model, we added more layers and accuracy is just above 61%. Since we use all of the images per patient, which includes low quality of images, we do not have a great accuracy. So we move on to next strategy. Strategy number 2, we use the best quality of the image per patient with image size increased to 500 times 500. The first model is VGG16. The accuracy jumps to just above 91%, which is 30% better than other models. Second model, we use a different transfer learning, which is Inception V3. Its accuracy becomes 94%, but the bottom plot shows a training saturated early stage. And after this model, we have tweaked a little bit differently. The third model, the accuracy went down. Even if we fix the early saturation, the final model we take is the accuracy just above 93% without early saturation. Since this is a medical research, we care about the false negative the most, which means we focus on the recall than any other metrics. In other words, we do not want to predict cancer patient as a normal patient. Here is our best model result. From now on, Jeremy takes over and talks about the production and demo.
Machine learning models exist to solve business problems, to drive impact. We wanted to showcase this with a mobile app that I created, but first, let's frame the problem and give it context. Dr. Fogleman, an oncologist at UCLA. He's participating in a department-wide initiative to collaborate with the data science team in developing this machine learning model. Unfortunately, this creates an extra workload, which sits on the back burner for several days as active patient care takes the priority. When the doctor can get around to evaluating his performance, the process is cumbersome. The image in question is sent via email along with the patient ID and the most current prediction results. However, if Dr. Fogleman wants to compare against the formal diagnosis, he must go to a separate Excel sheet, which is shared with the other participants via Dropbox. Furthermore, it's not always clear what the correct entry on the spreadsheet is that corresponds to a specific image. This requires the doctor to send an email to the data science team to confirm, and as a result, that specific validation is delayed, usually by several days. Mr. Cho, lead data scientist managing this team, notices his staff spends a significant amount of time on tedious tasks, such as tracking down images and scan results, validating the patient IDs are correct, identifying which doctors reviewed what specific image. Almost all of the communication is done sending emails back and forth. So in an effort to improve efficiency, the data science team has shared out this test information as an Excel spreadsheet via Dropbox. Unfortunately, medical staff has not adopted this solution and continues to rely on email. This now adds additional work for Mr. Cho, necessitating a manual search for the relevant details across all the email communication and then to consolidate it into this spreadsheet. Lastly, the model lives and executes on Mr. Cho's laptop. Translation, the model must be run manually and executed only while Mr. Cho is actively logged on. Chief Architect Mr. Otsap has had this drawn to his attention. He proposes using a mobile app as the front end for both the doctors and the data science team. This will streamline their collaboration, significantly reducing administrative efforts and manual tracking, allowing for quicker responses, and even maintaining a historical lineage. On the back end, leverage a big data platform, not your personal laptop. Now, while this is an oversimplification, adopting a big data platform such as Databricks offers beyond just the obvious improvements of raw compute performance and scale, things such as a centralized model repository for collaborative model development, tracking and versioning, and especially separating out the models from development from those in production. And also in this case, batch scoring on large data or image sets that can run automatically as a scheduled job. So with that, let's get into the demo. Now, first, let me preface this by saying I'm not an enterprise with an exhaustive budget. There are very real logistical and cost constraints that we could and could not deploy. It would have been spectacular to host our own Databricks cluster, but for purposes of the demo, we ran a batch and stored the results in a data table. So here you can see in the app a list of patient IDs. Note the personal identities are anonymized for HIPAA compliance, as well as facilitating any double-blind studies. As we are browsing patient records, we can visually distinguish those where the model's prediction was accurate versus those that had a conflict. So this item right here, the red test mismatch, is flagged on any test where the predicted result and the actual result do not match. So first, let's take a look at patient 24. We can see here the specific image view was an LCC. We can see the confidence from a rating of 1 to 5. We can also see the specific mammogram slice that was associated here. Now let's look at patient 13. Right away, the doctor can notice two visual cues to call to his attention. Firstly is the one we mentioned, the mismatch right here. But secondly, notice there is only one listing for patient 13 present. And recall, we mentioned earlier, each patient by default should have 4 different views. So it's possible other views needed to be discarded because they weren't associated with a biopsy result. And having 1 in 4 views could certainly affect the model's precision. So the doctor goes and investigates. So right away, we can see this is a type 1 error where a normal patient with no tumor is miscategorized by the model as having tumor. Looking at the image, perhaps the doctor sees something that the model might want to retrain, maybe this blotch right here. The confidence interval certainly isn't great. So given that, the doctor wants to flag this for further follow-up. So we can go in here to edit, and we can go into the rescan. We can change from no to yes, save that. Now, on the back end, this could be used to trigger another job to associate this image with a specific group of potentially difficult images that require closer inspection, whatever. It's a flag in a data field. So in conclusion, I want to reiterate, this is just a pilot. In a true production deployment, there would be other fields for tracking different departments or facilities, tracking what equipment had been used, and very likely some sort of approval process that would need to be integrated into this workflow. More than likely, there would be separate roles for managers, doctors, data scientists, and depending on that role, it would limit what fields you could or could not edit. So that's it. Thank you for your time.